Hello everybody, welcome to the webinar series Lubricants and Coolants, Part 1, Cold Rolling. My name is Arnold Uhl, I work for the company LUM in Berlin, Germany. This webinar series is a joint project of my colleagues Stefan Küchler, Sylvain Gracier and myself. There will be a brief introduction, then I would like to discuss step technology for particle and dispersion characterization with you, present case studies for lubricants for cold rolling applications. In the end, there will be a summary and an outlook. And during the separation, the change of transmission was recorded and quantified by integral transmission in easy words area below the curve as a function of time. We have here the plot of the analytical result obtained by LUM, the clarification speed, the change of transmission with time, versus customer's value for the conventional ESI. And we can see one lubricant is the most stable, one is in the medium range, and one is unstable. It is the identical ranking obtained now after 17 minutes, 11 times accelerated, and copied at the same temperature of 45 Celsius. Giving identical ranking of the lubricants also under different emulsion preparation conditions, which were not shown on the previous slide. Let's come to the second case study. Again, two oil and water-based emulsions, lubricants for cold rolling, were to be compared. First, by the determination of the droplet size distribution. Second, by the combination of different analytical methods for the reliable separation stability characterization of a challenging sample. Here we can see the results, the volume-weighted cumulative distribution curves. For the white lubricants, it's a perfect match of the duplicate. For the brown lubricant, we record few deviations between the two curves. Once we have a look at the median value, we determine 3.3 something micrometers for the white lubricant, and the median value for the brown lubricant is between 6.4 and 5.6 micrometers. There's also additional information available for the white lubricant. There was another method used, impedance-based method for particle size distribution characterization, and the X50 in the other method for the white lubricant was determined as X50 is equal to 3.5 micrometers, which is in good agreement with the LUMiSizer result. Let's come to the summary of the second case study, the white lubricant features. The droplet size distribution is narrower than of the brown lubricant. The median value X50 of the droplet size distribution is smaller. The instability index is tiny compared to the brown lubricant. By naked eye, before it is separated in an accelerated way, it appears homogeneous. After the accelerated separation, by using low relative centrifugal acceleration, it appears less separated. Compared to the brown, it is more stable against separation. The reliable characterization of lubricants, including challenging samples, consists of, we have the lubricant, we have always available the naked eye, we have the direct accelerated stability testing in the LUMiSizer, sometimes additional methods available, and the LUMiSizer is able to determine the droplet size distribution. So different views onto the same lubricant help us to understand and to characterize also challenging samples. Let's come to case study number 3. 6 different lubricants were to be compared qualitatively and in a quantitative way. And we get the following results. Instability index after 10 minutes. We have 2 samples with very high values. Sample number 3, 0.888, and sample number 6, 0.920. These 2 are the most unstable samples. Sample number 6 is the most unstable. Second unstable, sample number 3. The other 4 samples have changed and have smaller instability index values. They are much more stable than the 2. After 10 minutes, we are able to discriminate all 6 samples. But we can also learn that we need only 40 seconds for samples 3, 5, and 6. Same ranking, most unstable, sample number 6. Second most unstable, sample number 3. Third, number 5. Sample 1, 2, and 4 are close to each other, and here we recommend to run a few minutes longer, 40 seconds for the first 3, 10 minutes for all 6. The authors conclude there's a good correlation of the instability index with a separated oil and cream from emulsion obtained, and able to solve the problem of predicting the long-term rolling oil emulsion stability by this method. 6 hours in the LUMiSizer instruments versus 1 month storage in the hot air oven. It's much faster than conventional methods. It's more economic by saving time and sample amount. And last but not least, it's more environmentally friendly by using such smaller sample volumes and avoiding additional chemicals, avoiding the cleaning of sample containers and tools.
Hello everybody. The topic of our today's session is stability and particulate properties of high performance lubricants, a comprehensive characterization study. My name is Stefan Küchler. In the main part, we will present 2 case studies. First about stability analysis, second about particle droplet size characterization of high performance lubricants. Our first case study demonstrates the use of analytical centrifugation, so we can directly see here the propagation of the interface towards the filling height. What else can we see? As mentioned, from red to green, this is the measurement time color coded. We see also where is the filling height, the meniscus. We see that here there is some dropping down, means that there is also some very tiny creaming layer. On the right side, we have here indicated the clear phase and the cream layer, which is not yet compact. For more details on the procedure, I recommend our technical note at our platform dispersion letters. We look here at the time of 2002 because in the beginning there was no change between the samples. As we typically would like to differentiate also even more samples, which might be even more different in their stability. Therefore, here it makes sense to compare the samples after 1 hour, because then we have a much larger gap between the 2 curves. And that means that also in the bar chart, we have here a larger gap so that more samples could be effectively compared and differentiated. For these 2 samples, we get the same ranking. We apply again our instability index algorithm. That means we have the same region of interest applied to all samples as before. And now we see that we get here a nice ranking between the different samples. It's going up and down a little bit because the order of the samples is with increasing sample number. Lubricants ranking is confirmed by customers, not shown here. We get identical ranking regarding standard test procedures also for different emulsion preparation conditions. We get a fast ranking. We can lower the costs. We have a quick return of investment for the instrument. We have a low environmental impact. We continue now with our second case study. When we compare the left and the right sample, we see that here the spacing between the profiles is much, much larger. And this spacing is a direct measure of the separation velocity of the individual fractions of particles. As both pictures have been recorded under the same conditions, then we can also say, okay, if the spacing in the profiles is larger, there must be droplets of higher migration velocity in the left sample compared to the right sample. So we can do a reliable characterization of lubricants, including challenging samples, by different procedures. We have here independent results that we get from using the LUMiSizer, including velocity and droplet size distribution, including additional methods, including direct accelerated stability analysis, as shown before with the instability index, and also in agreement with visual inspection, which is always available. Independent results give identical ranking for heavy-duty lubricants. Also, an accelerated comparative shelf life in a few hours instead of months is possible with this instrumentation. The multi-wavelength approach, which is required, for example, if a broad range of extinction must be covered. They are faster than conventional methods. They are time-saving and anticipate long-lasting separation. They are environmentally friendly by using smaller sample volumes and avoiding additional chemicals, cleaning of samples, containers, and tools.
Topic of today, oil and lubricants and coolants how to analyze using LUM instrument. My name is Sylvain Gressier. I have the pleasure to be the animator of this session of today. I'm manager of LUM France. Case 1, you can have pure oil or concentrate oil, which typically are transparent. For that, you can use LUMiReader, a real-time analyzer, or LUMiSizer, an accelerated analyzer. Both are equipped with several wavelengths, and typically for transparent sample, we recommend you to use blue light source with an intensity of 0.5. Second state of dispersion. If you dilute your concentrate into water, you can have partly turbid samples. You can have also lubricants containing soot or nano after use in a motor, for example. And the creaming interface is moving from 130 to 120 for this surfactant. To be compared with others, all samples are measured on the same rotor, all measurements are perfectly synchronized, and you can compare the movement of the creaming layer with time just by overlaying the area under the curve of separation. You have a comparative method on the robustness and the performance of this surfactant. Just to give you an idea how it looks like, the milky emulsion was at the beginning white, and whilst the droplets are moving to the top, the bottom part is clarifying. Here you have the reference emulsions, and using a quantitative value on the creaming, you can say, okay, using those two surfactants, we have almost the same or even better robustness regarding the creaming. In simply 250 seconds, you can have a quantitative way to quantify the robustness. We can go even far into the quantification of this emulsion by displaying the creaming velocity of all the droplets. It's a polydispersed emulsion, so all droplets moving at the same speed, and instrument is recording the creaming velocity of each optical density into the sample, so we can have a quantitative way to measure the creaming rate of each class of the samples. And if we know the density, we can go up to the particle size distributions. If you compare that to what's happening at 50, here you have a real temperature influence of the evolution of this profile with the time. This concentrate is getting even more turbid. You have plus 20% in optical density. In terms of kinetics, with time, we can compare temperature at 20 and temperature at 50 degrees. It's almost 3 times faster when you increase the temperature of 30 degrees compared to 20. There is an evolution of this sample 3 times faster. So clearly here, this concentrate becomes turbid, and this is a problem for long-term stability. And typically when the oil is accumulating on top and on the bottom, you will see the two fronts coming from top and to bottom till full separation is reached. And this is typically a challenge to overcome for formulators to have stable oil mix. For that, we can offer you LUMiReader to quantify, because just to get a value for separation for this kind of sample, using eye only is almost impossible. So we provide you a solution to record, to trace, and to quantify the phase separation of this oil mix. This is what it looks like using an instrument. So the same video you've seen, here you have the record. We have a multi-wavelength system, LUMiReader or LUMiSizer, which enables you to analyze by boosting the power of the near-infrared light. This is how to fill the sample. Here you still have the graduation. Sample volume typically is 0.4 milliliter. Please keep in mind, LUM analyzer are solutions of choice for droplet sizing, direct and accelerated stability testing. It's faster than conventional methods. You need a very small volume and you use accelerated stress to quantify and to work on the sample. It's also very environmental friendly because the sample volume to be used is very low, 0.4 milliliter, remind.